where with the example that we left off with last class. No, Charlie, you don't even have to look at it. Like it's completely meant to just be an additional resource if you haven't seen CrowdMark before and you're a little nervous and you just want to get some practice. It's not for credit or anything like that. Yeah, you don't even have to open it. All right. Okay, so I wanted to start off going over a few of the details, the finer points of this exercise. So, am I recording here? Yes, okay, good. Okay, so one thing that often comes up at the start of Stat 252 is this concept of it being the beginning of it being review of 151 material, which is the case. Like this is meant to be review. All of these ideas you at some capacity you would have seen before. Now, some of the more technical parts of assignment 1, for example, question 8, where you have a confidence interval and a hypothesis test, these are things that I am going to go over in the second lecture set. So the focus of that entire lecture set is a review of the hypothesis testing and confidence interval process. So in some cases, you might already be comfortable with this. You might have notes from before where you can refresh them or review them and you'll be fine working through it. In other cases, I'll go over this stuff with you. One of the questions on assignment 1, I think it's the second question on assignment 1, asks for the differentiation between the parameter, the estimate, and the estimator. So I want to go over that now in the context of the question that's on slide 10, or the exercise that is on slide 10. So in this exercise, we have a data set that is composed of 20 values. Okay, so first off, these 20 values here, this would be the sample. So we have a sample with 20 observations in it. The part A of this question asks you to identify the population of interest. So the population of interest would be the collection of all final exam scores for some large introductory statistics class. So for this large class would be every single final exam score. And for whatever reason, we don't have that information, but that's what the population would be. Now, from the previous slide, slide 9, this slide differentiates between the symbols that we use for the parameter and the symbol that we use for the statistic. In the question below, part B, for example, it says, estimate the center of the population of interest and interpret your estimate. Okay, so just for some follow-up here, so this would be for part B. Let's say that our estimate of center, or the parameter of interest that defines the center, is the mean. Okay, so the parameter, which is the population quantity, is mu, which is the population mean, okay? So the symbol mu, the Greek letter mu, always defines the population mean. And in this particular problem, we're going to say that this is the parameter that we are interested in. The estimator, okay, this is effectively just the formula that we utilize to compute an estimate. So the estimator would be the actual expression x bar is equal to the sum from I equals 1 to n of xi over little n. Okay, so this would be our estimator. It's like the formula to find the estimate. And then the estimate would be the result which is that X bar is equal to 77.5, okay? And then again here, what X bar represents is the sample mean. Now I think there is a bit of confusion, and it's understandable between the estimator and the estimate because the symbol, the X bar, is being used in both. But the idea is that the estimator is effectively like the formula that takes in the sample to provide the estimate, which is the outcome of the formula. So similarly, in part C, if we were to do the same breakdown, the parameter is the population value, which is sigma squared. The estimator would be, it would be sigma, not sigma squared. We're doing standard deviation, right? So this is population standard deviation. And then the estimator is going to be the formula that we use. So for example, the sum from I equals 1 to n of xi minus x bar squared divided by n minus 1, right? So this is again the formula or the function of the sample that gives us our estimate. And then the estimate will end up being the value that is returned. So the estimate would be little s is equal to 17.606. So that's the distinction between them. And what you're being asked to do in question 2 is basically just create some, hypothetical situation where you define your own parameter of interest, and then you basically just pick an estimator that would work to get an estimate of that parameter, and then you would define the estimate, which is the outcome. You don't have to create data, but you can if you want to illustrate your point. But the idea here is basically just to describe a situation where these 3 things would apply. And in this particular slide, so on slide 10, where we had that exercise, basically that's an illustration of where you would have a parameter, which is the average exam score across all final exams in a stats course at some university. Your estimator will be the formula. X bar is the sum from I equals 1 to n of xi over n. And then your estimate would just be whatever you get out from the sample. And then you're just describing that collection, that process of moving from parameter to estimate, and also just distinguishing between each of the values and defining what they are. So that's the purpose of that illustration, or of that question. Any questions on that? All right. Okay, so if there's no questions, we'll continue to move on with the material. So the next thing that I want to talk about is the idea, or basically I want to build up to the definition of the central limit theorem. And this is kind of the starting point for all of our inferential techniques, because what this is going to allow us to do is understand the assumptions that are associated with the different hypothesis tests and confidence intervals that we are going to talk about in the upcoming lectures. All right. So first off, as we work up to this idea, we need to refresh some of our probability definitions. The first is the definition of a random variable. A random variable is a value that exists, but we haven't actually observed. So for example, on this slide, I have defined a random variable to be x. Capital X is said to be normally distributed from a population with mu equals 15, so that's the mean, and a standard deviation of 8. All right, what does it mean for X to be normally distributed? It's almost straight. Okay, what does this mean? What it means is that the value or the random variable x belongs to a population that admits a bell curve or has a density curve that is the shape of a bell curve. Okay, so one thing it means, x belongs to a distribution whose shape is a bell curve. Okay, so visually, what this would mean is the density curve for x is, okay, so we'll have a horizontal axis here. I'm just going to move this down. And then we have a bell curve. Let's make it bigger. And then we have a bell curve that sits on top of this horizontal axis. So the distribution to which x belongs admits this shape of a density curve. So its density curve is this bell curve. Now, what else can we say about this? 2, the curve is centered at mu with standard deviation sigma. So the middle part of the curve is mu, right? And then as we move away from mu in either direction, we have an equal amount of area. So we can actually define the amount of area that exists between one standard deviation of the mean on each side. So for example, here we have 0.34% of the area. And this is what is called the empirical rule. And then if we move 2 standard deviations over, okay, so here we'll have mu minus 2 sigma. In here we'll have mu plus 2 sigma. Okay, now in between the 2 standard deviations of the mean, we have, well, it's 95% total on each side, so that would be 47.5. Okay, so that is area under curve follows the empirical rule. Okay, and then if you move another standard deviation, so 3 standard deviations on each side, you then have 99.7% of the area. So for something to be normally distributed, what it means is that the distribution has a shape that is a bell curve. That bell curve is centered at the mean, and then you have equal distribution of area on each side of the mean to certain standard deviations from the mean. Now, something being normally distributed gives us a ton of ability to work with that value. We can find specific areas underneath the curve. So we can find the probability that the random variable is going to be between bigger or smaller than certain values. And we would do that using the standard normal table. It also allows us, in the context of hypothesis testing, to find the probabilities of observing certain events. So that is to find the p-values, which we can then use to make decisions about the questions that we pose in the hypothesis test. So the assumption of normality is a very powerful assumption, and it gives us a lot of ability as statisticians to make decisions about certain population quantities, in particular the population mean. All right, so we define the notation x x sim capital N 1564 to represent a random variable following a normal distribution with mean 15 and variance 64. So this part here, this is just a symbol saying x is normal with mu equals 15 and sigma squared equals 64. Okay, so that's just a shorthand notation for that idea. When we have a small x, we say that we have actually observed the larger value. This isn't something we need to dwell on too much, but the point is just we differentiate between what we actually see and what is considered random or unobserved by the case of the letter. Okay, so if we assume that the population we are working with is normal, when we collect a sample of values, so for illustration, in the exercise that we started off with today, we had a sample of 20 values. If we assume that all final exam scores are normally distributed, that sample is a collection of realizations from the larger population. Yeah, in some cases so the question in the chat is, will we have an option between the two? In some cases you will, and sometimes I'll ask you to give me a specific one. So you should be comfortable with both, and I'll demonstrate both once I get to that part. Okay, so when you collect a sample, you have a collection of values from that population. We would consider those to be realizations. Okay, so a question here, a very brief question, is just, if we collect samples of some size from an infinite size population, how many possible samples could we have? Okay, well, we would have an infinite number of samples. If you have a population with an undefined size or an infinite size, you can never run out of information, so you could have an infinite number of different samples. All right, so when you start from your population, you're going to say, we make an assumption that the population is normal most often, at least in the coming weeks, we'll make this assumption. You collect a sample, and now what you have is a sample of values that are also normally distributed. If I take from the normal, I have normal values. Now from that sample, we compute estimates. So we can compute the sample mean, we can compute the sample standard deviation, we can compute the sample variance. So the values that we talked about a bit at the beginning of the lecture, these are values that we can compute directly from our sample. Now, because the values in the sample follow the distribution, so that say our sample values are normally distributed, the sample mean, which is a function of those values, will also have a distribution. So the sample mean is also a random variable because its value will change with each of the different samples that we collect. It also follows that any other statistic that we build from a sample will also follow some distribution. So it'll also be a random variable. So that means that it's of interest to determine what the distribution of that random variable will be. Now, one of the main reasons why we want to know the distribution of the statistic that we are using, or of the estimate that we are using, is because we know that when we take a sample from a population, there has to be an error associated with that sample, because the sample is just a subset of the larger population. So the sampling error occurs as a result of us taking a smaller portion of the larger population and using that to build statistics and then inevitably conduct inference. So by learning or by being able to define the distribution of the statistic or the estimate that we are working with, we can then describe this sampling error. And this is very important to us because we do not want to misrepresent the results that we are giving. When you report things like averages without the associated standard deviation or the margin of error, if you will, it can be misleading. So being able to quantify this margin of error is actually very important in terms of providing reliable guidance, if you will, for maybe like policy making and things like this. Okay, so as I just said, the reason we would be interested in describing the sampling error is so that we can reliably give an interpretation of what we are observing in the population. So to give an informed interpretation of what we expect the population parameter to, I'll just write to be, though I'm not crazy on that particular phrasing. Okay, so at this point, what we have done is we've established that we have, in most cases, a population parameter that is of interest to us. Most often it'll be the population mean, which is mu. We define an estimator, which is usually going to be x bar is equal to the sum from I equals 1 to n of xi divided by n. So a formula. And then we compute an estimate using that formula by inputting the values from the sample. When we conduct inference, we assume that our population is of a certain type, usually normal. When we do that, it follows that the sample is also going to follow some distribution. If we sample from a normal, those values will also be normal. Our estimate is a function of the sample. So if our sample is a collection of random variables, then our estimate is now in itself a random variable. The reason that we would want to know the distribution of the random variable is because we want to describe sampling error, because we can't ignore the fact that this exists. So what is the distribution of, for example, the sample mean, which will be the estimate that we focus on most often? Okay, first off, to differentiate between the distribution of the population and the distribution of the sample, when we refer to the distribution of a statistic like the sample mean, we usually call that distribution the sampling distribution. So the sampling distribution of the sample mean refers to the distribution of the sample mean. Okay. Every single sampling distribution for the sample mean has two parameters with formula that do not change. So every single sampling distribution of the sample mean has a mean mu subscript x bar, and that's equal to the population mean. And it has a standard deviation sigma subscript x bar, which is equal to sigma over the square root of n. Okay, so these are the formula for the mean and standard deviation of the sample mean. Okay. And we can always utilize these formula. If we know mu and we know sigma, the population parameters, we can easily compute mu x bar and sigma x bar. All right, so what we have established right now is that the sampling distribution of the sample mean has two parameters associated with it. the mean and the standard deviation, which we call mu subscript x bar and sigma subscript x bar. What we can observe is that as sample size increases, the standard deviation gets smaller, right? So sigma x bar is equal to sigma over the square root of little n. As n gets larger, sigma x bar gets smaller, right? If we make the denominator of the expression bigger, we're just shrinking the result. So the bigger the sample size, the smaller sigma x bar. Okay, so what does this mean in the context of sampling error? Well, we have established that if we take a small, or rather, when we conduct inference, we have a population of interest, and from that population, we take a sample. If we take a really small sample, the standard deviation of x bar is going to be very large. Now, if we take a really small sample, we would also expect the sampling error to be very large. As we continue to increase sample size, the standard deviation of x bar is going to get smaller and smaller. Now, what we would also expect is that as we increase sample size, the sampling error is going to get smaller and smaller. So there's a relationship between the standard deviation of the sample mean and the sampling error, in that the standard deviation of the sampling mean in some sense allows us to describe the amount of sampling error. So this is a useful measurement for us. And what we can see is that the relationship between how this standard deviation behaves and how the sampling error behaves is effectively the same. Okay, so what is the actual shape of the distribution of the sample mean? Well, it turns out that if we actually sample from a normal distribution, this distribution of x bar, the sample mean, will also be normal. And this is just like a definition or a result, and it's a very useful definition or result. Now, the changes that we can expect in the distribution of the sample mean when we start from normal depend on the amount of information that we collect. So let's say that our population of interest is normally distributed with a mean of 70 and a standard or a variance of 100. Okay, so here is the histogram for the population. Now you can see that this histogram is admitting that bell curve-like shape that is associated with a normally distributed random variable. So we are centered at 70. Okay, so that's this line here. And then on each side of 70, we have on each side of 70, the amount of area is approximately equal. So these are the characteristics of a bell curve, which is what describes a normally distributed population. Okay, now what we're going to do is begin to collect observations or sample from the population and then compute sample means for each of the different sample sizes. So for example, let's suppose that we start by just collecting very small samples, so samples of size 2. So we collect some large number of samples, so say we have 1,000 samples of size 2, and then for each sample, we compute a sample mean, so now we have 10 or 1,000 sample means. And then we construct a histogram of that. Okay, so this is shown in the second illustration. So here we have sampling distribution of x bar when little n is equal to 2. Now again, what you can see here is that we are centered at the same point because the properties of the sampling distribution tell us that the mean of the sampling distribution is equal to the mean is equal to the population mean. Okay, so we're still centered at 70. Now we can also see that the histogram in this second plot is still a bell curve. But what's starting to happen here is that the peak of the bell curve is moving up and that the tails of the bell curve are moving in. Okay, so we have tails in and we have peak up. Right? Now, let's say that we redo the experiment. We collect 1,000 samples of size 5 for illustrative purposes, and then we compute the sample mean of those 5 observations. Well, here we now have the sampling distribution of X bar when n is equal to 5. So we have mu X bar is equal to 70. And then again, you can see the same relationship. So as our sample size increases, the tails move in and the peak is moving up. What this is showing us is that as we collect more information, the distribution of the sample mean becomes tighter to the mean, and that essentially represents accuracy within the estimate. So it's portraying the idea of a smaller amount of sampling error associated with the particular distribution of X bar, so the distributions of our estimates. And then finally, in the last plot, we have the sampling distribution of X bar when n is equal to 10. And then you can see all the same phenomenons, or all the same results, I should say, that we observed before. So what we have now established is that when I sample from a normal population, X bar is also going to be normal. So I have bell curve density curves for both the population, the sample values, and X bar. The distribution of X bar changes with sample size. The mean, the center of the bell curve, is always in the same spot, but the tails move in as the sample size increases. And this represents accuracy in the estimates, or in the distribution of our estimates of interest, which basically is saying that the more information we collect, the more accurate our estimate is going to be. Any questions? Well, I mean, in most cases, like in the practical problems, little n will be given to you. In this particular illustration, I just declared n beforehand, like just for illustrative purposes. Does that answer your question? Okay. All right. So we have established that if we start from a normally distributed population, that we are able to say that X bar is also normally distributed. Now, what does this allow us to do in the context of making statements about X bar? Well, one of the big thing, or in the context of making statements about the sampling error, I should say. Well, one of the big or most important things that we can utilize normality for is to make probability statements. In particular, we can use the property of normality to describe how we behave, how we expect the sampling error to behave. So for example, here, just one sec. Yeah. Okay, so for example here, what I have is, according to an article in the Journal of the American Geriatric Society, the standard deviation of the length of hospital stays on the intervention ward is 8.3 days. For all samples of size 80, what is the probability that the sampling error made in estimating the population mean length of stay is at most 2 days? All right, so what is it that we are being asked here? What we are being asked is, how likely is it that the error made in estimating mu is between 2 days? So this particular probability statement reflects being within 2 days of the true mean. Okay, so this is the probability that X bar is within 2 days of the population mean mu. Okay, now we are making the assumption that the distribution of stays on the intervention ward is normally distributed. Okay, so assume that distribution of length of stay is normal. So if the distribution of the length of stay is normal, then X bar must also be normal as per the definition that we have just described. So we can actually solve this type of probability statement by using the techniques that we established for normal curves beforehand. So X bar here is now normal. So since distribution is normal. So what that means is I can standardize X bar, or I can standardize the limits of the probability statement, and then I can just compute the probability of being within these 2 points. Okay, so from a visual point of view, I have the following. So this is the distribution of X bar. Okay. So in the middle here, okay. Wow. Okay, so this is the distribution of X bar. And then on each side of this, I have basically mu X bar plus 2, and then I have mu X bar minus 2. And what I'm trying to find here is the size of this area. Okay, so what is this equal to? How big is this area? Now I can draw this as a bell curve because, again, I'm assuming that the original population is normal. So by assuming that the original population is normal, that gives me the ability to write that X bar is normal, which means that I can sketch the sampling distribution in the following way. Now, when we work with normal random variables, what we then do is standardize our limits, and then we turn to the standard normal table. Okay. So recall that Z is equal to X minus mu over sigma. So if I replace X bar with X, or if I replace X with X bar, then I have Z is equal to X bar minus its mean over its standard deviation. So standardization is simply the process of subtracting your mean and dividing by your standard deviation. And this is basically what we do in hypothesis tests. When we compute a test statistic, that's really just a standardized mean. So now we're going to have x bar minus mu over sigma divided by the square root of n, because of the properties that we established beforehand when talking about the sampling distribution of x bar. All right, so in the above statement, what's happening here? So for example, if we consider this expression, we have z is equal to x bar minus mu over sigma divided by the square root of n. This is going to be mu minus 2 minus mu divided by 8.3 over the square root of 80, which are the values that are given to us in the problem. And then when we simplify this, we end up with that negative 2 over 8.3 divided by the square root of 80, which is negative 2.16. Okay, so that's how I went from the mu minus 2 to the negative 2.16. So again, what we're asking here is, under the assumption of normality, given a sample size of 80 and a population standard deviation of 8.3, what is the probability that the error made in estimating the population mean is within 2 days of the truth? So I can either be 2 days early or 2 days late. Now, because of normality, I'm able to progress in this way. So all of this work is a result of that normality assumption. Now, once I have the negative 2.16, the last part here is returning to the normal table and using the properties of the normal table to find the area underneath the curve. So if I return to the normal table here, okay, so I'm going to just take this part. Okay, so what I have boiled this down to now is I have a standard normal curve. I have negative 2.16 here. I have 2.16 here. And I want the following area. So these two areas are the same size. So the area here between negative 2.16 and 2.16, and the area between mu minus 2 and mu plus 2, those are the same size. Okay, so this is the probability that negative 2.16 is less than x is less than 2.16, which is going to be the probability x is less than 2.16 minus the probability that x is less than negative 2.16. Okay, so now if I just open up a normal table, and this is all stuff that we'll see examples of in the coming weeks when we talk about p-values as well, but just as a little bit of an early reminder. So I have 2 pages to the normal table. I have the negative side, and then I have the positive side. And the way that the table works is when I look up a bound on the axes, I get an area underneath the curve. And all of the areas are cumulative areas. So they start at negative infinity and they go up to the bound. So if I look up negative 2.16, which is here, I end up with 0.0154. And if I look up 2.16, which is here, I get 0.9846. So now the problem becomes 0.9846 minus 0.0154, which is 0.9692. And that's how you end up with the result that's given on slide 19. And again, all of this is meant to be a review of working with normally distributed random variables and working with the standard normal table. But the beauty of this is that given these distributional assumptions about the population, we can make these important statements about how we believe the estimates are going to behave. So if we start from normality, so a normally distributed population, and then we work our way towards a sample mean, we can say a lot about how we believe that sample mean is going to behave given a pre-specified sample size. So in this particular illustration, what we can say is that approximately 96.92% of all samples of size 80 will estimate the average length of stay within 2 days of the population mean. So every time we collect a sample of size 80, the probability that that sample returns an estimate, well, I shouldn't say that, but across repeated sampling, we expect that 96.92% of all samples of size 80 will estimate the mean within 2 days of accuracy, which is a pretty high percentage of the time. Now we can also write that there is approximately a 96.92% chance that the sampling error made in estimating the average length of stay using samples of size 80 will be at most 2 days. So these two interpretations given on slide 20 are talking about the same value, so they're from the same result, but it's two different ways of expressing the same idea. So we have one interpretation that's directly about the sampling error, and then we have another interpretation that I think is a little bit more easily communicated, that's talking about how we believe the sample mean is going to behave across repeated sampling. And this really starts to get up to the idea of confidence intervals and how we interpret confidence intervals and this kind of thing. Okay, so I just want to mention briefly in the couple minutes I have left here, the more realistic situation and the situations that we are going to start dealing with very often arise when the population is not normal. So for example, on slide 22, you can see a histogram of the population of the age of death of Australian males, and this is from 2012. Now, in general, the distribution for ages of death are always left skewed, and as time has progressed, the mode has pushed further and further or gotten higher and higher, which represents longer lives. But in this situation, our population is not normal. So the question is, if I start from a population that isn't normal, how can I still work with the sample and the sample estimates in a situation that is familiar and how can I still work with the values is essentially the question. Well, it turns out that as you collect more and more information from populations that aren't normal, you end up with sample means that return to normality. So in this illustration, in the first plot, I have that left skewed distribution. Okay, so here's the population. Now, as I've increased sample size, I've ended up with a sampling distribution, okay, for X bar that looks very normal now. So actually, what's very interesting is that the more information you collect from a population, regardless of the shape of that population, you return to a sampling distribution that is still normal. And this is what the central limit theorem states. Okay. So I'll stop here for today. And then on Monday, I'll pick up with this idea of the central limit theorem. And then we'll most likely move into the next lecture set to review hypothesis testing and confidence intervals. So have a good weekend. If you're interested in seeing some of the lab stuff, I'm going to be in that lab room at 2 p.m. Otherwise, this and that session will be posted on YouTube and whatnot. And if you have any questions, let me know. So I'll talk to you guys on Monday.